Hi, folks. This lesson is on the periodic table of elements. The original periodic table of elements was designed by Dmitry Mendeleev. Around that time, only about 60 elements were discovered, and scientists were in a race to put these in some kind of an order. And Dmitry Mendeleev, as you can see here, put those 60 elements, 60 or about that elements, in order of increasing atomic mass. So if you take a look at lithium at 6.94, 9.01, and you will see that the modern periodic table is slightly different in terms of its arrangement. But one of the big I guess, positives of his periodic table was the fact that he left blanks where he said new elements would be discovered. And he did that based on how the atomic mass was changing. So if you take a look at lithium at 6.94, 9.01, 10.8, you can see that it's changing for about 1.5 or whatnot. When you take a look at potassium, it's 39.1, 40.01, and then titanium was 47.9. So he said there is a big jump here, which means there's one element here that we have not discovered. And the same thing continued on the other rows here. So all these elements were discovered, and once these elements were discovered, then we put them in order of increasing atomic number now, and we came up with our modern periodic table. So one of the things you notice once again is that these are now all organized in order of increasing atomic number being the number of protons. We have the periodic table organized in two groups or columns, and we have, if you count, we have a total of 18 groups or 18 columns, and then we also have them arranged in rows, and there's a total of 7 rows. These last 2 rows, actually, if you take a closer look, the 57 and 89, they actually fit in here and in here. And the simple reason this was taken out, these 2 rows were taken out, is to make the periodic table a little bit narrower. These elements here, they're called the lanthanides and actinides, and we'll talk about them. You will learn very quickly that the columns, if elements are in the same column, typically they have a similar set of chemical properties. You will see the staircase here in and around here. So the elements that are in and around that staircase, so boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine, these are known as the semi-metal or the metalloids. And then anything to the left of that staircase here, these are all metals. And then to the right, these are what we call our nonmetals, and the nonmetals could be solids and they can be gases. But by a quick look at the periodic table here, you can see that we have way more metals in nature, in the universe, than we have nonmetals. So as I said earlier, if you are in a group, in most cases, you are part of a family or you have very similar chemical properties. So we give some of those groups names. So for example, group number 1, which by the way does not include hydrogen because hydrogen is not a metal, it's a gas. So starting from lithium down to francium, these are known as the alkali metals. And the reason we call them alkali metals is because when you place them in water, they produce what's called an alkali. It's called a soluble base. You don't know what that is. In later years in chemistry, you will learn what those are. Some examples are lithium hydroxide, sodium hydroxide, potassium hydroxide. Again, I don't want to bore you with that. Your group number 2 are your alkaline earth metals. Group 3 to 12 here in the middle are what we call transition metals. While we're talking about transition metals, these 2 rows here are what are known as inner transition metals or rare earth metals. In and around the staircase, we said we have the metalloids. The metalloids are also known as the semi-metals. And then group 17 here they're called halogens. And of course, lastly, the last group here are called the noble gases. So you'll see that we don't give a name to group 14, 15, and 16. So if you're a halogen, you are in group 17. The periodic table can actually be divided into 2 major groups. So all of these 18 groups can be subdivided further into 2 major groups. So groups 1, 2, 13, 14, 15, 16, 17, and 18 are what we call the main group elements. So typically, if you are in the lower grades, grade 9 and 10, you will be studying the main group elements. And then the transition metals are not part of that group. So if I say group, so typically you'll hear your teacher say group 5, group 6, they're talking about the main group elements. So what you will notice is when I teach, for example, in my class, I'll say that group 13 is actually group 3 for us. If group 14 is group 4, 5, this is 6, 7, and then 8. The reason we leave the transition metals out is that the transition metals have a set of properties that the rest of the metals don't have, or the rest of the elements don't have, and that's why we study these on their own. If you are taking IB or if you're taking grade 11 chemistry, you will dive more into the chemistry of these transition metals. So altogether we have 18 groups. Like I said, we can divide those 18 into main group elements and then the transition metals. So the main group elements here, that's group 1, that's group 2, that's 3, 4, 5, 6, 7, and 8. One of the things before we move on here is you would know about noble gases is the noble gases have complete outer shells. And what I mean by that is they have a full set of electrons in their outer shells, and that makes them energetically stable and non-reactive. A couple of things you should know here is that the group number, this is again, we're talking about the main group elements now, the main groups, which is groups 1 through 8, not including the transition metals. The group number tells us the number of valence electrons. So if you're in group 1, which is our group 1 right here, you can see hydrogen is not really part of the group 1, but it's placed in here because it only has 1 electron. So let's say from lithium down here, they all have 1 valence electron. You can see here's lithium with one of its valence electrons. Here's sodium with another valence electrons. These diagrams, by the way, you will remember from grade 9, they're called the Bohr-Rutherford diagrams. If you're in group 2, you can see here that you will have 2 valence electrons. And if you're in group 3, you'll have 3, so on and so forth. So this is 1 valence electron, 2, 3, 4, 5, 6, 7, and then 8. The only exception here in this column is helium, which has 2 valence electrons. But the reason it's placed here is because it's got 1 outer shell, 1 occupied outer shell. I'll explain what occupied is. And that shell is full. So if you guys remember from grade 9, the first shell can only hold 2 electrons. So if you have 2 electrons, that shell is considered to be full. Now, I wanted to point something out here is that every single atom here has an infinite number of shells or energy levels. So in chemistry, we only talk about the shells that have electrons in them. So for example, if you hear me say sodium has 3 energy levels, that's not entirely correct. Sodium has an infinite number of energy levels, but it only has 3 energy levels that have electrons in them. So this is why chemistry teachers, especially on the lower grades, typically talk about, fluorine has 2 energy levels. But just keep in mind that fluorine has more energy levels. It's only have 2 of those energy levels have electrons in them. The period number, and the period obviously is, if you go back to the periodic table earlier, is the rows going from left to right here. The number of rows, or the row number, will tell you the number of occupied energy levels. So in the case of, if you're in row 2, you will have 2 energy levels. And you can see all of these have 2 energy levels. If you're in row 3, these all have 3 energy levels. One of the things you will learn as you're going through chemistry is something called Lewis dot diagrams. And again, this is drawn for the main group elements. The Lewis dot diagram shows the symbol and the number of valence electrons. Again, if you are in the first group, you will have 1 valence electron. If you're in the second group, you will have 2 valence electrons. If you're in the third one, so on and so forth. This is very, very handy. This is just a shorthand way of writing the number of valence electrons. The valence electrons you'll see when you start talking about reactions and chemical bonding, the valence electrons are the most important ones because those are the ones that are involved in bonding. What I mean by bonding is when atoms come together and form compounds. So that, for example, when the 2 hydrogens come together and form water with oxygen, it's these you will see when we talk about bonding, these Lewis structures or Lewis dot diagrams are quite handy. One of the things you will notice here is that we put a single electron on each side before we start pairing. So if you have 4 valence electrons, you got 1, 2, 3, 4. Now if you have 5, you go 1, 2, 3, 4, then you start pairing. Now, the pairing is very, very important here. You will see that in the case of fluorine, for example, these halogens would have 7 valence electrons. They have 3 paired electrons and they have 1 unpaired electron. So the unpaired electrons here are quite important. I don't want to bore you with them right now, but keep in mind that this has 1 unpaired electron, this one has 2 unpaired electrons. It's the unpaired electrons that are typically involved in chemical bonding. The last thing I want to talk about is something called ions. So if you don't know what ions are basically charged atoms. Atoms are typically neutral because they have the same number of protons and electrons. So if the number of protons and electrons is equal, the atom is electrically neutral. Now, if I were to change the number of electrons, then the atom can either become positively charged or negatively charged. Keep in mind that an atom can only lose and gain electrons, not protons, because protons are stuck inside the nucleus. So if an atom was to lose electrons, it would form a positive ion. So if you take a look at this example here, beryllium with a 2 positive charge, that basically means that beryllium lost 2 electrons. Now, if you don't remember that, or if you haven't done this, then your teacher will do this in more detail with you. But essentially what this means is that beryllium had equal number of protons and electrons, but now, for whatever reason, beryllium has lost 2 electrons, and because it's lost 2 electrons, it has 2 extra protons, and because of that, it has a 2 positive charge. Let's take a look at an example here very quickly here. So sodium, if I take a look at sodium has 11 protons and it has 11 electrons, my bad, when it is completely neutral. So 11 positive and 11 negative, obviously that adds up to 0. Now, if for whatever reason sodium were to lose 1 electron, now sodium has 10 electrons. You can see here that I have 11 positives and 10 negatives, so I have 1 extra positive. Because of that 1 extra positive here, now sodium has a 1 plus charge. If you take a look at this side, on this side here, on the right side of the periodic table, you can see that now I see negative charges here. The negative charge basically means that fluorine here, for example, has picked up 1 electron. If you have a charge of 2 minus, that means you have picked up 2 electrons. So just to quickly summarize here, you will see that the elements that are metals, so the ones on the left side of the periodic table, are the ones that are typically forming your positive ions. Some of them actually have multiple positive ions. The fancy name for positive ions are cations, and the fancy way, or the not fancy, but the chemical or chemistry name for them are cations, and for the negative ones, they're anions. So the metals are the ones that typically form cations or positive ions, and the non-metals are the ones that typically form anions. And you lose electrons by forming cations, and you gain electrons by forming anions. Now, why do they do this? Well, this is something that you will learn as you go through bonding. These elements are all trying to become stable, like these noble gases. Notice that noble gases are all grayed out, which means they don't form any ions. They actually don't bond very easily. All the other elements here are trying to become stable, and essentially what that means is that they're trying to get their outer shells to be complete, or they have a full octet or 8 electrons in their outer shell. So, quick summary of what we learned. The modern periodic table is arranged in order of increasing atomic number. The group number tells you the number of valence electrons. The period number tells you the number of energy levels with electrons in them. Lewis dot diagram shows the number of valence electrons. Metals lose all their outer electrons and form cations. These are the positive ions. And then non-metals typically gain electrons and form anions.